Ancient stonework achieves a precision that challenges our most advanced tools. This is not a story of primitive technology, but of forgotten methods that somehow outperformed modern engineering. Civilizations across the globe, from the deserts of Egypt to the highlands of South America, worked stone with a mastery that baffles experts today. By the end of this journey, you will understand how 10 lost techniques created results our lasers and diamond saws struggle to match. We will uncover how sound could carve rock and why some stones appear to have been softened like clay. What does our struggle to replicate the past reveal about the true nature of human innovation? Deep within the Bolivian highlands lies a field of shattered stone that whispers of a forgotten science. Puma Punku is not a grand pyramid, but a labyrinth of granite and diorite blocks, each one a geometric puzzle. The sheer complexity is staggering, with stones cut into perfect H shapes, L shapes, and interlocking channels that fit together with seams thinner than a razor blade. These are not rough constructions. The surfaces are flawlessly flat, the corners are perfect 90-degree angles, and the edges are sharp enough to draw blood. Some blocks even contain drill holes that plunge deep into the stone with a consistent, machine-like precision. Modern engineers struggle to explain it. How could a culture without iron tools, let alone electricity, achieve a level of workmanship that today would require computer-controlled machinery? The conventional narrative of slow, manual labor with stone hammers and copper chisels shatters against the evidence at Puma Punku. This was not crude construction. It was a form of high technology, and we have yet to rediscover its most basic principles. The mystery of Puma Punku points toward a single, radical possibility. What if the stone itself was not carved but shaped as if it were something soft and pliable? The first lost method we must confront is the idea of megalithic stone softening. This theory suggests ancient builders possessed a substance, perhaps derived from plants, that could temporarily alter the very structure of granite, making it as workable as wet clay. Historical records from Spanish conquistadors in South America contain startling accounts. They wrote of the Inca using a mysterious liquid applied to the surfaces of massive stones that allowed them to be fitted together without mortar. The blocks would seemingly merge, the seams becoming so tight that not even a blade could slip between them. This was not just stacking, it was a form of molecular stitching. Modern science offers a glimpse into how this could be possible. Experiments with organic acids found in certain local plants have shown they can chemically react with the crystalline structure of granite, essentially breaking down the bonds between mineral grains on the surface. This creates a softened, paste-like layer. A worker could then mold that surface, press another stone against it to achieve a perfect fit, or polish it to a mirror shine with minimal effort. After a period of time, the chemical would dissipate and the rock would return to its original, legendary hardness. This process would explain the impossible. It accounts for the flawless, flowing curves on granite boxes, the intricate interlocking channels that look molded rather than cut, and the complete absence of tool marks that should be everywhere. A diamond-tipped drill today slowly grinds its way through the same stone, a violent and slow process, but a chemical softener would allow for a gentle, almost artistic shaping, achieving a level of precision and efficiency that our loud, powerful tools cannot match. The implications are profound. It means these builders were not just master craftsmen, they were early chemists with a deep, intuitive understanding of geopolymer science. They knew how to talk to the stone to convince it to change its form. We are only now beginning to decipher the language they spoke. The idea of softening stone challenges everything we assume about the past, but it is only the beginning. Another method emerges not from chemistry, but from the air itself, from the silent power of vibration. Legends from across the globe speak of cultures that moved and shaped colossal stones using nothing but sound. Tibetan monks are said to have used long horns and deep chanting to levitate blocks into place. Stories from ancient builders describe drums and specific tones that could make massive rocks glide across the ground as if weightless. For a long time, these accounts were dismissed as pure myth. Yet modern physics is now revealing a startling truth: sound can indeed command stone. Scientists have demonstrated that every material has a natural resonant frequency, a specific pitch at which it vibrates most easily. When sound waves of that exact frequency are focused on an object, the energy transfers directly into it, causing the material to vibrate intensely. At a high enough amplitude, this sonic energy can create microscopic fractures within the rock, effectively causing it to come apart along precise, internal fault lines. This is not brute force, it is a delicate unraveling. Imagine a skilled singer shattering a crystal glass with the perfect note. Now envision that principle applied with immense control to a block of granite. The stone would not be cut so much as it would be persuaded to separate, leaving behind a surface of impossible smoothness. This concept of sonic carving offers a compelling explanation for some of the most perplexing ancient stonework. Consider the massive, intricately shaped blocks at sites like Olantaytambo in Peru. Some surfaces have flowing, concave cuts and inner corners that would be incredibly difficult to produce even with today's diamond-tipped routers. A waterjet cutter, our modern tool for precision stone cutting, uses a high-pressure stream of water and abrasive grit to slowly erode a path. This process, while accurate, leaves a slightly textured surface. A blade of pure sound, however, would leave no such mark. By finding the resonant frequency of the rock, an ancient craftsman could guide a fracture line through the stone with sub-millimeter accuracy, creating a finish as smooth as glass without any physical contact at all. The implications point toward a lost branch of physics, an intuitive mastery of harmonic technology. These builders may have understood the world as a symphony of vibrations, and they learned to compose with it. They did not fight the stone's hardness, they listened for its song and then joined in, using that knowledge to achieve a silent, clean precision that our loudest, most powerful tools still struggle to replicate. This was not magic, it was applied science of the highest order, and if sound could carve, what else could it do? The very movement of these multi-ton blocks presents the next great puzzle, one that leads us to a forgotten art of transportation. The silent power of sound gives way to a third method, one that harnessed the very essence of the earth itself. Ancient artisans did not just listen to the stone, they learned to fight it with its own kind. Crystal-aided abrasion reveals a world where primitive tools achieved a level of precision that can still make modern engineers pause. At the heart of this technique was a simple yet brilliant understanding that to cut the hardest stone, you needed something even harder. Builders from Egypt to South America turned to nature's own super abrasives, materials like quartz crystal and diamond dust. These were not exotic imports in the way we think of them today, but locally sourced, crushed minerals that gave ordinary tools extraordinary power. The evidence for this is etched indelibly into history, most clearly in the artifacts of ancient Egypt. Massive granite boxes and statues show the unmistakable marks of tube drilling. These are not rough, chiseled holes, they are deep, cylindrical bores into solid granite, and inside them you can still see the consistent, spiraling grooves left by a rotating tool. This is not the work of a man hammering a copper spike. It is the signature of an advanced rotary process, a technology we thought was millennia away. So how did they do it with what we consider primitive means? The answer lies in a deceptively simple combination. A copper saw by itself is soft and would barely scratch granite. But when that same saw is pulled back and forth, fed with a wet slurry of sand and water, a transformation occurs. The sand, which is primarily quartz, acts as millions of microscopic cutting teeth. Each grain of quartz is harder than the copper, but also harder than the feldspar and mica within the granite. As the saw moves, these hard particles embed themselves into the softer copper, creating, in effect, a self-renewing blade coated in countless diamond-like edges. This blade then slowly, patiently, grinds its way through the stone, one microscopic grain at a time. The process is slow, but it is incredibly controlled and gentle on the material. Modern power tools, for all their speed and force, have a significant drawback: heat. A diamond-tipped saw or drill spins at high revolutions, generating intense friction and thermal stress. This heat can actually damage the crystalline structure of the granite, causing microfractures and a weakened, sometimes burnt, edge. The ancient method of crystal abrasion, however, used the constant flow of water and sand to keep the cutting surface cool. It removed material through a steady, cold grinding process that left behind a cleaner, stronger, and often more polished cut than many of our loudest machines can produce today. This was not a lack of technology, it was a different kind of technology altogether. It was a patient, symbiotic relationship with the environment. These artisans were not overpowering the stone with brute force, they were persuading it to open up, using the Earth's own crystals to reshape the Earth's own bedrock. They achieved a quality of work that we, in our rush for speed and power, sometimes overlook: the enduring value of a perfect, stress-free cut. The patient art of crystal abrasion gave way to a method of raw, elemental power. Fire and water, the most basic forces of nature, became precision instruments in the hands of ancient engineers. This is the principle of thermal shock, a technique that harnessed the violent physics of expansion and contraction to command the very bedrock. Across ancient quarries, from the mountains of Peru to the deserts of Egypt, you can still find evidence of this practice. The faces of cliff sides are scarred with long, straight fissures and the remains of hearths, telling a story of controlled demolition. The process was deceptively simple yet required profound observational skill. Workers would build hot fires directly against the natural rock face. As the flames grew, the outermost layer of stone would expand from the intense heat. Then, at the critical moment, they would douse the heated surface with water or perhaps even vinegar, causing that expanded layer to contract violently and instantaneously. This rapid temperature change created immense internal stress, forcing the rock to fracture along a clean, predictable plane. This was not random cracking. It was a calculated act of geological surgery. By controlling the placement and intensity of the heat, they could guide the fracture line, effectively persuading a multi-ton block to separate neatly from the living mountain. This method of thermal shock quarrying was astonishingly efficient. It left behind minimal rubble and waste, preserving almost the entirety of the valuable stone. Compare this to a modern quarry that uses dynamite or jackhammers. Those powerful methods do break the rock, but they do so with brute force, shattering the surrounding material and creating a massive amount of irregular debris and microfractures within the stone itself. The ancient thermal technique, however, produced a clean, structurally sound block, ready for transport and finishing with far less subsequent labor. The sophistication of this approach reveals an intuitive, almost innate grasp of thermodynamics. These builders understood the personality of the stone they worked with, knowing how different types of granite or limestone would react to the treatment. They were not just laborers, they were early physicists who learned to read the language of heat and stress. They achieved a level of material preservation and efficiency that our most powerful explosive methods sacrifice for speed. This lost art of fracturing rock with fire and water stands as a testament to a different kind of intelligence, one that worked in harmony with the Earth's own forces to achieve a goal with breathtaking elegance and precision. But the power of fire and water was not the only great force these builders mastered. they learned to harness the strength of living beings to drive machines of stone. The fifth lost method reveals a world where animal power fueled precision engineering. Long before the steam engine, civilizations like the Romans employed vast, sophisticated systems in their quarries, powered not by coal or electricity, but by the patient, immense strength of oxen. Historical accounts describe these animals walking in endless circles, turning massive wooden capstans. This was not simple pulling, it was the heart of a mechanical system. The rotation of the capstan could be transferred through gears and axles to operate heavy stone-cutting lathes and polishing wheels. The oxen provided a steady, relentless torque, a form of biological engine that could run for hours, shaping and smoothing the hardest granite with unwavering consistency. This consistent power was the key to their incredible finish. When combined with the abrasive slurry of sand and water, the animal-driven lathes could polish a stone surface to a mirror-like sheen. The result was so flawless that it required no additional work by hand. The stone emerged from this process perfectly finished, its surface sealed and hardened by the meticulous grinding. This animal-powered machinery achieved an efficiency that often surpassed the earliest industrial machines of the 18th and 19th centuries. Those early steam engines were notoriously inefficient, consuming vast amounts of fuel for a relatively small power output. The biological engine of an ox, however, converted locally available forage into direct mechanical work with a remarkably small environmental footprint. There was no smoke, no coal dust, and the primary byproduct was natural fertilizer. This was a sustainable technology perfectly adapted to its time. It represents a brilliant fusion of animal husbandry and mechanical innovation, a system where living muscle was integrated into the manufacturing process to achieve a level of quality and scale that still commands our respect. The quiet, patient turn of the oxen in the quarry created a legacy of stone that has endured for millennia, a testament to an era where power was not just measured in horsepower, but was literally provided by it. The steady rhythm of animal power finds its parallel in the fluid intelligence of water. The sixth lost method flowed directly from the landscape itself, harnessing rivers and canals as natural cutting tools. Near many ancient megalithic sites, archaeologists have uncovered intricate networks of channels and basins, long dismissed as simple irrigation. But a closer look reveals a different purpose. These were the power sources for advanced hydraulic workshops. The principle was one of relentless, gentle force. A controlled flow of water was directed to turn a large wooden wheel. This wheel, connected by a series of gears and cranks, could then power multiple stone saws simultaneously, pulling long, abrasive-coated blades back and forth across a block of granite with the steady, unwavering pace of a river. This was not just a faster version of manual labor, it was a fundamental leap in manufacturing consistency. The continuous flow of water solved two critical problems that plagued hand-powered cutting. First, it automatically supplied a fresh, cool, abrasive slurry to the cutting surface, washing away the ground-up stone debris that would otherwise clog the blade and slow the work. Second, it eliminated the human element of fatigue and inconsistency. A team of workers might slow down or change rhythm, but the water wheel provided a perfectly uniform stroke, hour after hour, day after day. This unwavering mechanical patience produced a result that stuns modern surveyors: perfectly flat surfaces on a massive scale. When laser levels are placed against the faces of certain ancient granite blocks, they reveal a geometric precision that is almost unnerving. The surface is not merely flat to the naked eye, it is planar to within a fraction of a millimeter over many meters. This is a level of accuracy that speaks of a process governed by unchanging physical laws, not variable human effort. Our modern diamond wire saws, for all their speed, are incredibly energy-intensive and require constant monitoring. The ancient water erosion system, by contrast, was a masterpiece of sustainability. It used a renewable natural force to do the heavy lifting, required no fuel beyond the river's current, and created a closed-loop process where the water and abrasive could be recycled. This method did not conquer nature, it collaborated with it, achieving a silent, efficient, and flawlessly precise result that stands as a quiet rebuke to the noise and waste of our own industrial power. The silent, flowing power of water gives way to a technology written in the stars themselves. High above the noise of quarries and the flow of rivers, ancient builders found their ultimate guide. The celestial dome became their most precise tool, a fixed reference point for achieving architectural perfection on a scale we can scarcely comprehend. Structures from the Giza Plateau to the Andean highlands are not randomly placed. They are meticulously oriented to the movements of the sun, moon, and specific stars with an accuracy that defies simple explanation. How could cultures separated by oceans and millennia achieve such consistent alignment without satellites or global positioning systems? The answer lies in a profound and patient understanding of the night sky. These master architects used the heavens as a giant, immutable protractor. By carefully tracking the rising and setting points of a star like Sirius, or marking the exact location of the sun at the summer and winter solstices, they could establish a true north-south or east-west axis with astonishing precision. This was not a single measurement, but a ritual of observation repeated over generations, refining their knowledge until the cosmic patterns were etched into their cultural memory. This astronomical calibration translated directly into the stone. The Great Pyramid of Giza, for instance, is aligned to the cardinal directions with an error of less than 1/15 of a single degree. To put that in perspective, modern surveyors using advanced theodolites would struggle to achieve such perfection over such a vast base. The builders did not have lasers, but they had something perhaps even more reliable: the unchanging mechanics of the solar system. This cosmic connection provided a foundation of absolute truth from which every right angle, every straight wall, and every geometric proportion could be derived. The integration of sky knowledge with earthly construction represents a holistic genius. It was not merely about building a tomb or a temple. It was about anchoring human achievement within the cosmic order. The structure itself became a terrestrial mirror of celestial harmony, a permanent testament to a culture's understanding of its place in the universe. This method achieved a level of precision that was not just technical, but spiritual, creating monuments that have resisted not only the ravages of time, but also the limits of our own modern understanding. They built with the stars as their blueprint, and in doing so, they created a legacy that continues to silently challenge our assumptions about the past. The cosmic precision of the stars finds its earthly echo in the very materials of life. While celestial alignments guided grand designs, the intricate assembly of individual stones required a different kind of genius, one written not in the sky but in wood and hide. The eighth lost method points to the use of biological template systems. Consider the staggering walls of Saxehuaman in Peru. These are not simple straight lines. They are vast, undulating curves with colossal blocks of limestone carved into bizarre, multi-angled shapes that lock together in a monumental stone puzzle. Each stone is unique, a custom-fit piece with as many as 12 distinct contact surfaces, all meeting its neighbors with a seam so tight that even after centuries, you cannot force a piece of paper between them. How could such chaotic complexity achieve such perfect order? The answer may have been temporary, organic, and has long since returned to the earth. Ancient builders likely created full-scale templates from pliable materials like wood, leather, or even woven plant fibers. A master architect would first design the wall's sweeping curve on a smaller scale. Then, craftsmen would transfer that design to the ground at full size, using stakes and ropes to outline the shape. From this outline, they would construct a flexible wooden formwork that mirrored the exact, complex negative space a specific stone needed to fill. This formwork was not a rigid mold, but a guiding pattern. Masons would then rough-cut a new stone block and repeatedly test its fit against this biological template, shaving and grinding away tiny amounts until the stone slid perfectly into its designated place. This system allowed for the transfer of incredibly complex, non-repeating geometries from a design plan directly into solid rock with astonishing fidelity. It was an analog form of three-dimensional printing, using decomposable materials to achieve a permanent result. Modern digital modeling can certainly design such a wall, but physically replicating it with computer-controlled machines is a slow, expensive process of custom cutting every single block. The ancient method, however, was elegantly efficient. It decentralized the work, allowing many teams to work simultaneously on different stones using simple, reusable guidance systems. The true brilliance lies in the material choice itself. Wood and leather are forgiving, they can be adjusted and refined as needed. They represent a flexible intelligence, a collaboration between the rigid permanence of stone and the adaptable, living world. This approach did not fight the stone's irregularity, it celebrated it, creating a structural resilience that sheer, straight walls could never offer. Each perfectly fitted stone distributes weight and withstands seismic shocks far more effectively. The builders of Saxehuaman were not just stacking rocks, they were weaving a fabric of stone, using temporary biological tools to create a permanent masterpiece of engineering. The intricate stone puzzles of Saxehuaman lead us to a profound question. How did ordinary people, without cranes or computers, place these colossal blocks with such breathtaking precision? The answer may lie not in forgotten technology, but in a forgotten form of collective human intelligence. This ninth method reveals that organized human coordination could achieve a level of sensitivity and adaptability that rigid machines still struggle to replicate. Experiments with modern teams have demonstrated something remarkable. Using nothing more than guide strings, wooden rollers, and a system of chanted calls, groups of volunteers can maneuver multi-ton stone blocks into a final position with an accuracy of just a few millimeters. This is not a chaotic heave-ho. It is a symphony of synchronized effort where each person becomes a single sensor in a vast, living system. One person watches the alignment from a distance, calling out minute adjustments. Dozens of others feel the subtle shifts in the ropes, responding with tiny, coordinated pulls. The entire group moves as a single organism, guided by tactile feedback and shared focus. This human wave approach leverages something that a robotic crane simply does not possess: distributed intelligence. A machine follows a pre-programmed path, but it cannot feel when a stone hesitates on a pebble or sense the slight binding of a roller. A team of people, however, can instantly adapt. They can compensate for an uneven patch of ground, ease a block over an obstruction, and collectively feel their way to a perfect fit through a constant, silent conversation of touch and tension. The social organization required for this precision is itself a sophisticated technology. It reveals management and communication techniques that enabled collective craftsmanship to far surpass what any individual could accomplish. A master builder did not need to micromanage every move. Instead, they established a clear system of roles, signals, and shared understanding. This created a resilient workforce where knowledge was embedded in the group itself, not just in a single leader. The result was a living, breathing precision instrument, capable of achieving a gentle, nuanced placement that our most powerful hydraulic arms would perform with jarring force. This lost art of collective effort reminds us that human collaboration, when perfectly orchestrated, can be the most advanced tool of all. It builds not just with stone, but with shared purpose. This final method requires us to look not at the tools, but directly at the stone itself. Ancient builders possessed a deep, intimate understanding of the living earth, a geological intelligence passed down through generations. They did not see a granite cliff as a monolithic obstacle, but as a complex material with its own internal logic and predictable behaviors. Certain varieties of granite and limestone contain natural crystalline structures that cleave along specific, invisible planes. A master quarry worker knew exactly where to place a series of wooden wedges. They would soak these wedges with water, and as the wood expanded, it would exert a gentle, immense pressure, not to smash the rock, but to encourage it to part along its own natural line. This was a conversation with the material, a request for it to open up. The resulting split was so clean and precise it often required no further finishing. The stone was born from the mountain already perfectly shaped. This geological wisdom stands in stark contrast to the approach of a modern diamond-tipped saw. Our powerful tools do not ask, they command. A diamond blade spinning at furious speeds essentially pulverizes a path through the stone's crystalline structure. It achieves a straight cut through overwhelming force, but it wastes material, generates dangerous dust, and can create microscopic fractures in the surrounding stone. The ancient method of controlled fracturing, however, worked with the stone's inherent grain. It was a form of finesse that resulted in a stronger, structurally superior block, shaped with an efficiency that minimized waste and respected the integrity of the material. What we see in these ancient quarries is not just evidence of labor, but a library of accumulated observation. It represents centuries of watching how rain eroded certain outcrops, of noticing how frost cracked one type of stone but not another, of learning the unique song each rock would sing when struck with a hammer. This was a science rooted in patient, direct experience with the natural world. They achieved their legendary precision not by fighting the character of the stone, but by truly understanding it. In our rush to dominate materials with power, have we forgotten how to listen to them? This lost dialogue between human and rock may be the most profound secret of all, a reminder that the greatest precision often comes not from force but from knowledge. This comparison forces us to question the very definition of progress. Take the task of drilling a single, deep hole into solid granite. A modern CNC machine, equipped with a diamond-tipped drill, accomplishes this with blistering speed. It spins at thousands of revolutions per minute, grinding its way through the stone in a matter of hours, a task that would have taken ancient artisans weeks. On the surface, our victory seems absolute, but if we look closer at the results, the story becomes far more nuanced. Inside the modern drill hole, you will find a surface that is microscopically rough, almost gritty, from the violent pulverization of the crystal structure. The intense friction generates significant heat, which can actually weaken the granite along the edges of the cut. Now, examine the interior of an ancient Egyptian tube drill hole, like those found in granite sarcophagi. The spiral groove left behind is not rough but almost polished. The ancient method, using a copper tube and an abrasive quartz sand slurry, was a cold process. It gently abraded the material away one tiny crystal at a time, preserving the stone's inherent strength and leaving behind a flawlessly smooth finish that required no additional polishing. For this specific measure of quality, the so-called primitive technique produced a materially superior result. The ancient approach valued the integrity of the stone itself, achieving a perfection we often sacrifice for the sake of velocity. This pattern extends beyond simple holes to the creation of complex shapes. A modern CNC router is unparalleled at carving intricate, repeating patterns or perfectly flat surfaces. It is a master of Cartesian geometry, of straight lines and perfect circles defined by digital code. But ask that same machine to produce the irregular, multi-angled, and organically curved blocks that form the walls of Saxehuaman, and its efficiency plummets. Each uniquely shaped block would require custom programming and a slow, meticulous cutting process for every single face. The ancient system of biological templates, however, thrived on this complexity. By using flexible on-site guides, teams could work in parallel, custom fitting each stone with an adaptive intelligence that a pre-programmed machine lacks. The modern tool excels at repetition, while the ancient method mastered adaptation. This reveals a fundamental trade-off. Our technology prioritizes speed and replication for standardized tasks. Theirs prioritized a deep, almost symbiotic understanding of the material and the final form, achieving a level of custom-fit precision and structural resilience that is incredibly difficult to automate. It is not that one is universally better, but that they represent different philosophies of creation. We built a world of powerful, fast tools that conquer materials. They forged a world of patient, intelligent methods that collaborated with the stone. The real mystery is not which was better, but what we lost when we chose power over partnership. The perfection of these stone walls stands in silent contrast to the human world that built them, a world far more fragile than granite. How could such sophisticated knowledge simply vanish from the earth? The disappearance was not a single event, but a slow unraveling caused by profound social shifts. Consider the collapse of sprawling empires like the Roman Empire. These were not just political entities, they were vast, interconnected economic networks. Specialized stoneworkers depended on a steady flow of commissions from temples, monuments, and public works funded by the state. When the empire fractured, that economic foundation crumbled, grand construction projects halted, and the demand for master artisans evaporated. The intricate, multi-step processes for working granite were no longer a valuable trade. They were a useless luxury in a world focused on basic survival. The knowledge did not disappear in a fire, it faded away from simple neglect, no longer practiced because it was no longer needed. This technological regression reveals a painful truth: advanced societies are not immune to forgetting. The specialization of labor, often a sign of progress, created a critical vulnerability. A master stone carver knew how to shape a block from quarry to final polish, a holistic understanding of the entire craft. But as societies grew more complex, labor became divided. One group quarried, another transported, and another did the fine carving. This division increased efficiency, but it also compartmentalized knowledge. No single person held the complete mental blueprint for the entire operation. When the system collapsed, the fragments of knowledge, scattered across different trades, could not be reassembled. The complete methodology was lost. Further eroding this knowledge base were periods of intense cultural and religious change. With the rise of new faiths across the ancient world, many older pagan traditions and their associated building practices were actively suppressed. The master artisans who served the old gods often found their skills suddenly outlawed or rendered socially unacceptable. Their sacred geometry, their understanding of celestial alignments for temple construction, and their secret formulas for stone softening compounds were driven underground. These were not secrets written in easy-to-hide books. They were living traditions passed orally from master to apprentice in a sacred trust. When that chain was broken, when a master died without a student to receive the knowledge, it died with them forever. This was a loss of wisdom, not just technique. We are left with a profound lesson about the nature of complex skills. They are not merely collections of data. They are living cultures that require a community to sustain them. A single book on crystal abrasion cannot teach the feel of the stone, the sound of a correct fracture, or the intuitive timing for a thermal shock. That tactile, experiential wisdom is the true heart of the craft, and it is the first thing to evaporate when a tradition is interrupted. The silent stones they left behind are more than monuments. They are a warning about the fragility of our own collective knowledge, and a reminder that the most advanced tools we possess are not made of metal but of memory. This gap between ancient mastery and modern assumptions has not gone unchallenged. For decades, a small group of researchers and stonemasons has taken to quarries with a simple mission: to put these theories to the test using only the tools and materials available in antiquity. One of the most prominent figures in this field of experimental archaeology is a master stonemason named Roger Hopkins. On various television programs, he demonstrated time and again that what seems impossible with primitive tools becomes remarkably achievable with the right technique. In one memorable experiment, he aimed to cut a straight, clean slice through a block of granite. The modern expectation would demand a diamond-tipped saw. Instead, Hopkins used a simple copper saw, a bag of sand, and a steady stream of water. With patient, rhythmic strokes, the copper blade, charged with sharp quartz sand, began to bite into the stone. It was not a fast process, but it was a steady one. After hours of work, the granite block was severed, revealing a cut that was not just functional, but surprisingly straight and smooth. The real revelation was not the tool itself, but the immense skill required to use it effectively. The angle of the stroke, the consistency of the abrasive slurry, and the reading of the stone's grain were all critical. This was not unskilled labor, it was a performance of deeply ingrained knowledge. Another experiment focused on moving massive weights. The conventional image involves thousands of slaves straining against ropes. Yet Hopkins and his team showed that a much smaller group could move a multi-ton stone block with astonishing control. They used wooden rollers lubricated with water and a system of levers and pivots. With coordinated pushes and the strategic placement of guide logs, they could steer the colossal weight with a precision that rivaled modern machinery. The key was not brute force, but an understanding of physics and friction, and a synchronized human effort that acted as a single, intelligent machine. These modern trials consistently highlight a factor our technology often renders obsolete: the human element of patience and practiced skill. Our power tools deliver immense force instantly, but they do not possess the subtle feel of a craftsman who understands exactly how much pressure to apply or the moment to add more water to the cutting slurry. This lost knowledge was not merely a set of instructions, it was a physical wisdom held in the hands and the eyes of the artisan. The struggle to perfectly replicate the finest ancient work, like the mirror finishes or the perfect 90-degree angles, reveals the depth of that sophistication. We can mimic the actions, but we are still relearning the intuition. These experiments do more than just test historical methods. They quietly challenge our cultural obsession with speed and power, suggesting that some forms of precision were born not from overwhelming force, but from a harmonious collaboration between human, tool, and material. The silent endurance of these ancient stones holds a secret our own modern constructions have yet to learn. When we look at a 4,000-year-old granite surface, still holding a mirror polish, we are witnessing more than just skilled craftsmanship. We are seeing a profound understanding of the stone itself, a knowledge of how to preserve its integrity for millennia. Modern engineering often focuses on immediate strength and speed of production. We pour concrete that sets in hours and fabricate steel beams designed for specific load limits. But this approach can overlook a critical factor: the long-term behavior of materials. How will these substances react to centuries of temperature cycles, moisture, and the subtle, relentless stress of gravity? The ancient artisans were not just building for their own time, they were building for eternity, and their work reveals a forgotten science of material longevity. Take the legendary polish on an Egyptian granite coffin. After thousands of years, its surface remains flawlessly smooth, resistant to dust accumulation and environmental wear. A modern polished granite countertop, by contrast, will lose its high shine over a matter of decades, requiring resealing and repolishing to maintain its appearance. The difference lies not in the stone, but in the final molecular handshake between the tool and the material. Recent microscopic analysis has uncovered a startling truth. Certain ancient polishing methods, likely involving fine crystalline abrasives and patient, consistent pressure, did more than just make the stone shiny. They actually altered the crystalline structure at the very surface of the granite. This process created a layer of compressive stress, a kind of invisible shield that pushes inward against the stone. Think of it like pre-stressing a balloon. When you blow into a balloon, the rubber stretches outward, creating tensile stress that makes it prone to popping. But if you could somehow force the surface molecules to squeeze together, you would create a compressive stress that makes it far more resistant to tearing. This is precisely what the ancient methods achieved. By cold working the surface with abrasives, they locked the top layer of crystals into a state of compression. This compressed skin actively resists the formation of microcracks, the tiny flaws that are the starting point for all material failure. Water cannot seep in, frost cannot expand, and the slow creep of crystalline deformation is effectively halted. Modern industrial polishing, for all its speed, often does the opposite. High-speed diamond pads generate significant heat through friction. This thermal shock can actually induce tensile stress on the surface, pulling the microscopic crystals apart and creating a network of invisible weaknesses. The stone looks perfectly polished to the naked eye, but it has been subtly compromised, making it more vulnerable to staining and long-term degradation. This ancient insight is something our own material science is only now rediscovering at the frontiers of nanotechnology. Today, engineers are developing techniques to induce beneficial compressive stresses in metals and ceramics to dramatically improve their fatigue life and durability. We are learning through advanced computation what the ancients knew through patient, tactile experience. The true lesson from the stone is not about a specific tool, but a different philosophy. It is a reminder that the most enduring results come not from dominating a material, but from understanding its inner nature and working in concert with it to unlock a strength that time itself cannot easily erase. This drive for perfection was never just about engineering. It was a spiritual act. For the ancient mind, the universe was a sacred, ordered whole, and their temples and monuments were mirrors of that divine harmony. Mathematical precision in stone was not a technical achievement. It was a moral and spiritual one, a way of aligning human creation with the unshakable laws of the cosmos. The slight misalignment of a wall was not merely a construction error, it was a philosophical failure, a dissonant note in a celestial symphony. This profound belief system created a cultural environment where patience was a virtue and attention to detail was a form of devotion. A modern construction project is governed by budgets and deadlines, where time is money and good enough is often the goal. But for the builders of a pyramid or a sacred wall, the project was an act of worship that could span generations. There was no financial incentive to cut corners, only a spiritual imperative to get it right. The work was not a job, it was a legacy, a permanent offering to the gods, and a testament to a civilization's understanding of its place in the grand design. This fusion of art, science, and faith created a unique crucible for craftsmanship. The stonemason was not just a laborer, he was a participant in a grand cosmological ritual. His ability to shape a stone to a perfect 90-degree angle was not merely a skill, it was his contribution to maintaining the balance of the world. This philosophical foundation empowered artisans to push their craft to levels that seem superhuman to us today. They were not building for a client, they were building for eternity, and that single, powerful idea may have unlocked a depth of focus and a reservoir of patience that our modern, commercially driven world struggles to comprehend. The stones they left behind are not just puzzles of engineering. They are the physical manifestation of a forgotten relationship with the universe, one where precision was the highest form of prayer. That spiritual patience translated into a form of economic efficiency we have almost entirely forgotten. The true cost of a stone monument is not measured in hours alone, but in the total energy and resources consumed from quarry to completion. A modern diamond wire saw slicing through granite is a spectacle of power, but it is also a massive consumer of electricity. The energy required to run the industrial motor, to cool the blade, and to power the entire support system adds up to a significant financial and environmental bill. Furthermore, this violent process generates a constant stream of stone dust and slurry, a fine, abrasive waste that must be carefully managed and disposed of, adding another layer of cost and complexity. The ancient method of crystal abrasion, by contrast, used a copper saw powered by human muscle and fed with simple sand and water. The energy input was entirely renewable, sourced from the food the workers ate. The abrasive sand was locally gathered and could often be reused, and the only byproduct was a harmless, silty water that could settle and separate, leaving minimal trace. There was no electricity bill, no fossil fuel consumption, and no hazardous waste. The slowness of the cut was not inefficiency. It was the natural pace of a system designed for minimal resource drain. This principle extends to the monumental task of moving stone. A modern crane lifts a 100-ton block using diesel fuel or grid electricity, a one-time burst of concentrated, non-renewable energy. The ancient technique of using wooden rollers and levers, powered by coordinated teams of people, converted sustainable biological energy into mechanical work. The fuel was grain and legumes, and the system created zero emissions. When we calculate the full life cycle cost, the picture becomes startlingly clear. The modern approach is built on a foundation of high energy density fuels and centralized power, which gives it incredible speed but makes it vulnerable to resource scarcity and price shocks. The ancient system was decentralized and resilient, powered by sources available in any village. Its currency was not money, but time and communal effort, resources that were perpetually renewable. For a society building for the ages, this long-term sustainability was the ultimate form of efficiency. The stones still standing today are a testament to a different economic logic, one that valued permanence and harmony with the environment over the fleeting advantage of speed. This deep, embodied knowledge was never meant to be written down. It was a living craft passed from one set of hands to another through the most sophisticated learning system ever devised, the Master-Apprentice relationship. Imagine a young person spending not just years but decades working side by side with a master artisan. They begin by performing the simplest tasks, mixing the abrasive slurry or fetching water. Over time, they graduate to holding the drill steady, learning the precise angle and rhythm needed for a clean cut. They are not just learning steps from a manual, they are absorbing a universe of subtle, unspoken cues. They learn the sound of granite when the cut is going well, a quiet, grinding hum. They learn the feel of the saw when it begins to bind, a slight vibration in the wood handle. They learn to judge the consistency of the abrasive paste by its color and texture. This is tactile knowledge, a wisdom that lives in the muscles and the senses. It becomes so ingrained that the artisan does not need to consciously think about each movement. Their body simply knows how to respond to the material. This embodied mastery allowed for a level of real-time problem-solving that is incredibly difficult to code into a machine. A modern CNC machine follows a pre-programmed path. If it encounters an unexpected hard spot in the granite, it will simply push through, potentially damaging the tool or the stone. A master craftsman, his hands feeling the subtle change in resistance, would instantly adjust. He might change the angle of the stroke, add more water to cool the cut, or switch to a finer abrasive. He is in a continuous, silent dialogue with the stone, and his decades of embodied experience give him the vocabulary to respond. This multi-generational chain was the true engine of refinement. A master would spend a lifetime accumulating small innovations, little tricks of the trade that made a cut cleaner or a polish brighter. On his deathbed, his most valuable possession was not a tool, but this accumulated wisdom which he would pass to his most promising apprentice. That apprentice would then build upon that foundation, adding his own discoveries, and pass an even richer body of knowledge to the next generation. This is how techniques were perfected over centuries, not through sudden invention, but through the slow, steady accumulation of nuanced understanding. The loss of these extended learning systems represents a profound gap in our modern approach to skill. We often seek to codify everything into manuals and digital instructions, but in doing so, we leave behind the ineffable, the intuitive, the deeply human elements of craft that separate simple work from true mastery. We gained efficiency and scale, but we lost the living thread that connected the wisdom of the hands directly to the material world. Even the most trusted evidence can hide a secret for centuries. We have long studied the tool marks on ancient Egyptian stone vessels, assuming they were the simple result of hand-held drills and chisels. But a new kind of vision is transforming this old story. High-resolution, three-dimensional scanning technology is now mapping these surfaces with an almost impossible precision, revealing details invisible to the human eye. The data paints a startlingly different picture. The spiral grooves left inside granite vases are not wobbly or irregular as you would expect from a handheld tool pressed by human strength alone. Instead, they are mathematically consistent, showing a feed rate and rotational symmetry that could only come from a machine with a fixed axis and a mechanically driven cutting head. This is the signature of a compound machine, a lathe or a drill press that could hold the workpiece and the tool in perfect, stable alignment. The implications are staggering. It suggests the existence of sophisticated workshops, powered by water or organized teams, where stone was turned and shaped with a level of mechanical assistance we only attributed to the Industrial Revolution. This was not just a man with a bow drill, it was a system. The ancient artisan was an operator, guiding a process that harnessed mechanical advantage to achieve a flawless, automated finish. These digital scans force a humbling realization. For over 100 years, we looked directly at the proof and misinterpreted it because it did not fit our narrative of technological progress. We saw primitive handiwork where there was actually the ghost of a machine. This ongoing detective work at dig sites and in labs continues to unveil surprises, proving that the story of ancient innovation is far from complete. The true scale of their capabilities is only now coming into focus, one microscopic groove at a time. These perfect stone joints and celestial alignments point to a hidden language, a silent mathematics etched into the very bones of the earth. The builders did not need laser rangefinders or digital calipers because they were fluent in the universal grammar of geometry. Their measurement system was not based on fixed units like inches or centimeters, which can be lost or distorted. Instead, it was built on proportional relationships, a system of ratios that remains true regardless of scale. A master architect might define the entire plan of a temple using a single, repeated ratio, perhaps the square root of 2 or the golden mean. Once this foundational relationship was established, every single element, from the grandest wall to the smallest decorative niche, was derived from it. This created a structure where every part was in perfect harmonic conversation with the whole. You can see this principle in action at a site like the Temple of the Sun at Machu Picchu. The trapezoidal shapes of the doors and windows are not random. They are all expressions of the same angular relationship, a recursive pattern that ensures visual and structural harmony throughout the entire complex. This is a form of embedded intelligence. The design rules are baked into the geometry itself, so even a junior mason following the proportional template would naturally create a piece that fit perfectly into the grand scheme. This approach eliminated the need for constant remeasurement and minimized cumulative error. In our modern construction, we build piece by piece, checking each element against a separate, absolute standard. A tiny imperfection in one brick is compounded by the next, leading to deviations that must be corrected later. The ancient method, however, was self-correcting. Because every element was derived from the same proportional seed, the entire structure grew organically toward a predetermined state of perfection. They were not assembling blocks, they were growing a building from a single mathematical idea. This holistic precision created monuments that feel alive, their proportions so naturally balanced that they seem to resonate with a hidden order, a silent music built from stone. This profound adaptability meant there was no single secret to their success, but rather a whole library of techniques, each one perfectly matched to its environment. The ancient builders' first question was not which tool was most powerful, but what the local landscape itself could provide. In the rainy highlands of Peru, where water was abundant, they perfected hydraulic systems, channeling rivers to power their stone saws. Yet in the arid deserts of Egypt, where every drop was precious, they turned instead to the sun and sand, mastering the thermal shock of fire and the patient abrasion of wind-blown quartz. Their toolkit was not a standardized catalog of imports, but a curated selection of whatever worked best right where they stood. This was engineering by context, not by convention. A modern diamond saw operates with the same roar and speed whether it is in a Brazilian quarry or a Scandinavian workshop. It is a universal solution, but its efficiency depends entirely on a universal supply chain for fuel, spare parts, and energy. The ancient methods, by contrast, were self-contained and locally sustainable. A water-powered saw in the Andes stopped working if the river dried up, but it required no imported diesel or complex machinery. Its limitations were dictated by the natural world, and its builders planned accordingly, creating a resilient system deeply rooted in its specific place. This place-based innovation led to solutions that were not just effective, but often superior in their long-term results. Consider the granite of Aswan used for Egypt's obelisks. Its particular crystalline structure made it ideally suited for thermal shock quarrying. The builders knew that heating and cooling would cause it to fracture along clean, predictable lines. Attempt the same technique on a different type of granite from, say, Scandinavia, and the result might be a pile of useless rubble. The ancient artisans possessed this geological intuition. They understood the unique personality of their local stone, knowledge gained through generations of trial, observation, and passed down wisdom. Our modern universal tools lack this nuanced understanding. They apply overwhelming force to conquer any material, but in doing so, they often fail to bring out the best in any specific one. The ancient approach was a form of collaboration with the local environment. They did not seek to overpower the challenges of a specific location, but to listen to them and find the most elegant path through. This contextual intelligence created structures that have endured for millennia, not in spite of their surroundings, but because they were born from them. That intense, sustained focus was its own form of invisible technology. We often picture ancient artisans engaged in brute labor, but the reality was a state of deep, meditative concentration. Operating a hand tool for hours on end required a mental discipline that modern machine work largely bypasses. A person guiding a copper saw through granite entered a kind of flow state. Their entire awareness narrowed to the feel of the tool, the sound of the cut, and the visual feedback from the stone. This was not a distracted mind. It was a mind perfectly attuned to the task, capable of perceiving the most subtle signals from the material. A slight change in the pitch of the grinding sound indicated a shift in the stone's density. A subtle vibration in the wooden handle signaled that the blade was beginning to bind. The artisan, in this heightened state of awareness, would make an instantaneous microscopic adjustment, changing the angle of the stroke or the pressure of their hand. These were corrections so small and so immediate they were more reflex than conscious thought. This continuous dialogue between human and material created a quality of work that is fundamentally different from machine output. A modern CNC machine is programmed to follow a set path with immense power. It does not feel the stone. It does not listen. If it encounters a hard spot, it simply pushes through, potentially damaging both the tool and the workpiece. The ancient craftsmen, by contrast, collaborated with the stone. Their focus allowed them to work with its unique character, not against it, navigating its internal landscape of crystals and fissures with a gentle, intelligent touch. This suggests that true tool mastery was as much a cognitive development as a physical one. The years of apprenticeship were not just about building muscle memory, but about cultivating a specific quality of attention, a patience and presence that allowed the artisan to become a seamless extension of the tool itself. The flawless surfaces they left behind are not just a record of their skill, but a fossilized imprint of a profoundly focused mind. This ancient dialogue between human and stone is no longer confined to the past. Across the globe, a quiet revolution is underway as modern architects and engineers look backward to build a more resilient future. They are weaving these rediscovered methods into the fabric of contemporary sustainable design, creating structures that are not only efficient but profoundly durable. In regions frequently shaken by earthquakes, this return to tradition is proving its worth in the most dramatic way. The legendary stone walls of Saxehuaman, with their intricate, interlocking blocks, have withstood centuries of seismic activity that would reduce a modern reinforced concrete building to rubble. The reason lies in that very complexity. A rigid concrete frame, when shaken, tends to crack at its stress points and collapse, but a wall of perfectly fitted, multi-angled stones behaves differently. When the ground moves, the individual blocks in such a wall can shift and slide minutely against one another, dissipating the earthquake's energy as friction. The entire structure flexes and settles like a puzzle adjusting itself rather than fracturing. This inherent flexibility is a form of ancient seismic engineering that we are only now fully appreciating. This wisdom is being applied in projects from Peru to Japan, where traditional dry stone masonry techniques are being revived and hybridized with modern materials. Engineers might use a core of reinforced concrete for initial stability, but then clad the structure in a skin of custom-fitted stone, creating a building that combines modern tensile strength with ancient compressive intelligence. The result is a hybrid approach that leverages the best of both worlds, the speed and initial strength of industrial methods with the long-term resilience and sustainability of artisanal craft. This fusion underscores the enduring, practical value of this lost knowledge. It is not a romantic homage to the past, but a clear-eyed recognition that for certain challenges, especially those posed by a changing climate and unstable ground, the old ways offer solutions that are both elegant and extraordinarily effective. The stones have been speaking for millennia, and we are finally learning to listen again. Our relentless drive for speed has created a kind of technological tunnel vision. Modern engineering, for all its brilliance, operates within a framework of specific cultural and economic priorities that can act as blinders. We celebrate what is fast, what is standardized, and what can be easily scaled up for mass production. In this race for efficiency, any process that requires significant time, deep skill, or adapts to local conditions is often dismissed as primitive or impractical. We have been conditioned to see technological history as a straight line of improvement, where the new automatically supersedes the old. This linear narrative causes us to overlook the profound advantages of methods that operate on a different set of principles. Consider the modern assembly line, a marvel of standardization. It produces thousands of identical parts with incredible speed, but it struggles immensely with customization. An ancient workshop using biological templates, however, was a master of bespoke creation, where every single stone was a unique piece of a larger puzzle. Our system is optimized for repetition. Theirs was optimized for resilience and perfect fit. The economic pressure to deliver quick returns on investment further entrenches this bias. A construction project today is governed by strict budgets and timelines. The idea of a project spanning multiple generations, with artisans patiently refining each block, is economically inconceivable in our current model. We have prioritized immediate cost savings over long-term durability, choosing materials and methods that are good enough for a few decades rather than perfect for millennia. This focus on short-term gain has blinded us to the full lifecycle cost of our own technology. The energy consumption, the waste byproducts, and the eventual need for replacement or repair are often externalized, not factored into the initial price. The ancient approach, by contrast, was inherently sustainable, with its energy sourced from food and water, and its waste being minimal and natural. This is not to say one system is entirely better than the other, but that our singular focus on one definition of progress has caused us to dismiss a whole library of alternative solutions. The quiet perfection of ancient stonework challenges the very core of our assumptions. It suggests that innovation is not always about moving forward in a single direction, but sometimes about understanding the depth of what was already achieved. By recognizing our own technological blind spots, we open a door to a more nuanced and humble view of history. It encourages us to look back not with condescension, but with curiosity, asking what we might rediscover and integrate into the future of how we build. The silent perfection of these ancient stones is not a closed case but an open invitation. The most exciting chapters in this mystery are being written right now in laboratories and remote workshops around the world. One of the most promising frontiers is microscopic analysis. By examining tool marks at a nanoscale, researchers can now distinguish between the unique signatures left by a diamond saw, a copper blade with sand, or even a chemical softening agent. Each method leaves a different fracture pattern in the crystalline structure of the granite, a tiny fingerprint that could finally confirm which techniques were truly used. This is not just about identifying tools, it is about reading the very language of the cut, understanding the precise sequence of actions an artisan took thousands of years ago. Alongside this digital detective work, experimental reconstruction offers a hands-on path to the truth. Teams of archaeologists and skilled stonemasons are building full-scale replicas of proposed ancient machines, from water-powered saws to massive animal-driven lathes. The goal is not just to see if they work, but to measure everything: the time required, the wear on the tools, the quality of the final finish, and the total energy expended. Only by physically recreating these processes can we understand the true balance of skill, patience, and ingenuity they required. Perhaps the most vital source of insight comes from the living keepers of stoneworking traditions. In a few isolated communities, particularly in parts of South Asia and the Andes, artisans still practice methods passed down through countless generations. Studying their oral histories, their specific chants for moving stone, and their intimate knowledge of local geology could reveal nuances that no laboratory instrument can detect. They hold a tactile wisdom, an embodied understanding of how to listen to the rock. The future of this research lies in weaving these threads together. An archaeologist's find, a materials scientist's microscope, and a traditional artisan's hands must all meet. This interdisciplinary dialogue is our best hope for finally hearing the full story these stones have been trying to tell us. The mystery endures not as a failure of modern science, but as its greatest inspiration, pushing a new generation to look beyond power and rediscover the profound intelligence of partnership.